Hey guys, Jordan from Storage Review. Vince and I are out here in Pangbourne, the UK at the Castrol Liquid Cooling Center of Excellence. They've got all kinds of stuff going on here, from the fluid dynamics to the chemistry that goes into keeping the fluid clean. They're testing cables, they're testing server components, and they've got these test cells where they're doing all this. First up, we've got our GRC test cell that we'll take a look. We've got our Isotope test cell as well. We've seen Isotope before. That's the rack level kind of immersion where each server is individually immersed. The GRC is a tank-based system. Moving further along, we've got our Castrol branded Submarine tank. This is one of their smaller applications in here. Again, this is a tank scale thing. This is a very small version of it, but we've got something special outside that we'll take a look at later related to that. And then of course we've got AirSys, which uses a rack level vertical submersion system. The servers are actually in there on an angle and the fluid flows off of them. We've got a lot of ground to cover in this video, so make sure you grab a cup of coffee, hang out, and join us for the fun. We're gonna be talking from fluid viscosity to the chemical additives that go into the fluid. We're going to talk about the environmental impacts of this, how they manage the fluid from its entire life cycle, from when it's first manufactured to when it's redeployed after processing. And we've got this Submarine Megapod. This bad boy is a drop-in data center that uses liquid immersion cooling on the inside. They've got a couple racks in here with some test gear in it. We'll take a look at that. Right now, it's a standard UK day. It's starting to rain a little bit, so let's head inside and take a look at all the cool stuff and start deep diving on the technology. Here inside the Submarine Megapod, we've got two of the SmartPod XLs. That stands for extra large. That means there's a lot of room inside these guys. Castrol's currently testing out two liquids. This is their DC-15 liquid. You can see that these servers are plugged in, they're operational. Wires are put in specific spots to avoid wicking of the fluid. They've got everything thought out and well designed. There's an overhead crane for removing them. And then down here, we've got a second SmartPod XL, and this is using the DC-20 liquid. They're validating that the cables don't deteriorate, that the fiber optics don't deteriorate, that there's no interference or anything like that, that all of the different stuff on the server boards, from the plastics to the connectors, doesn't have any sort of negative impacts from the fluids. But essentially how this works is this is a 42U rack and there's a CDU on either end of it. The fluid is circulated around on the inside, and there's a heat exchanger in both of those that plumb out to the facility water, whether it's a megapod like this where everything is self-contained and there's a cooler on the roof, or you've got a larger facility. These SmartPod XLs are able to plug in and keep the systems cool and operating. Out here on the roof of the Megapod, we can see where all of that heat ends up going. There's a couple options that they can do with the heat that comes out of those systems. Now remember, this isn't the fluid that's in the tank that's up here. Running through these pipes is a glycol mixture that interacts with the CDU heat exchangers inside the SmartPods. So up here, we've got a couple different ways to deal with the heat. This big box next to me is actually a heat exchanger that could be used for heat rejection out to some sort of recovery, whether it's in-floor heating or some sort of building heat, or exchanging it out to a pond, or maybe I can get one of these and keep my pool warm during the winter. This pump, which is remarkably quiet and is running right now, is currently configured and running the coolant through this heat exchanger. They've got a couple different ways they can supplement for very hot days, but right now there's just some fans pulling air through and it's pulling the heat out of there. They don't need to do extensive cooling. We don't need to do any sort of chillers or refrigerant cooling because of that fluid temperature being able to operate in that 40 to 50 Celsius range, which is still adequate to keep the servers cool. There's not a lot of environments where you would need to add refrigeration cooling to this, except for maybe the most extreme, but for 99.9% of the world, this is all you need. And it's an extremely quiet solution considering how much compute you could pack into this Megapod. All right, so to tell us a little bit more about where we're at, what we're doing, and what's going on here, we brought in Nick Barrett from Castrol. Nick, good to see you. Thanks for having us out. What can you tell me about what we got going on?
Yeah, great to see you. Good for you to be here. So welcome to Castrol's Liquid Cooling Center of Excellence. In this facility, the way we've gone around this is to have individual rooms where we can do testing on tanks, systems, hardware, whatever it might be. Each of these rooms has temperature control so that we can maintain the ambient conditions, ventilation and fire suppression so that we can test fluids of today, but also research fluids of tomorrow, ones that might come under a bit more safety stringent testing regimes. So here you can see a GRC tank.
Yeah, it's got a cool green glow to it.
Yeah.
Looks pretty on brand.
Exactly. So within this tank is our fluid. In the tank you can see servers that are undergoing Testing, so we're currently testing for compatibility, interoperability, making sure they perform as intended under the fluid. So this falls into our position to have fully tested and validated technology stacks.
I see GPUs in here too, so those just work when you get them immersed, they're good to go?
Yeah, so these GPUs have been through a slight adaptation. So that means that they've had the thermal paste removed from inside and replaced for a different thermal interface material.
So that's an interesting point that you bring up. What changes have to be made to what components in order to be ready to go into an immersion cooling system?
Yeah, not too much. It's quite a simple process actually. So what we see is you remove the heat sinks from the CPU and clean the thermal interface material, the paste away. That's not compatible with immersion cooling. It simply just washes off.
Okay.
So we see what's typically used is indium foil, and there's also some other thermal interface materials available that is coming out on the market. It's a good area for research. Also with the GPUs, a very similar process. So they just get taken apart, thermal interface material changed for something that is compatible for immersion, put back together, away you go.
What about like the thermal pads and stuff that we see, like usually on GPUs and stuff around the VRAM and stuff like that? Do those pads have to be changed out to something that's compatible?
So it depends what they're made. If they're gel pads, then yes.
Okay.
But it's a good area for research. Lots of research going into thermal interface materials for immersion.
Still an emerging technology, right?
Yep.
Okay. But applicable today, there's obviously, it works.
Solutions ready to go.
Yeah. Cool. And then we've got, I see there's cables in here. These look a little nicer than the junk I'm used to seeing.
Yeah, so these are polyurethane cables. They are compatible with immersion, as are the Ethernet cables as well.
So we've got the GRC tank here. It's a little warm to the touch actually, which is kind of nice. It's been chilly out today. What's the thermal capacity of something like this?
So this tank can handle 50 kilowatts of power using high water inlet temperature. If you use refrigeration in a cold water inlet temperature, you can handle higher heat capacity. But for our scenarios, it's set up as a 50 kilowatt tank. And around the back here, you can see our heat rejection circuit. So our secondary circuit, our water glycol circuit, is fed out to a dry cooler. Our dry cooler has 100 kilowatts of capacity, so that feeds 2 of these test cells.
Okay.
And there's no refrigeration cooling in here either. So because of the high heat of the dielectric fluid, we can handle dry cooling, free cooling year round.
So talking through these with like serviceability, like how hard is it to work on these after they've been in the fluid?
Not too difficult as far as I'm concerned. It's a slight different process from working on an air-cooled environment or direct to chip. It's a bit of a mindset change. But once your facility's ready for immersion cooling, it's quite a simple process. The servers can be lifted up using a crane or a jack or a hoist, and then you can either work on them directly there while it's overhanging the tank, or you can simply remove it, take it off to a workbench.
Well, can we do that?
Why not?
All right. Well, Nick, you got me all dressed up here in my fancy Castrol lab coat. What are we going to do?
I could always do with a pair of hands. So today you're going to come and help me do some maintenance on a server in an immersion environment.
Oh, wonderful. I've wanted to do that. Well, we saw our tanks here, we saw our waterfalls there, but I see all kinds of fun noises coming out of this room here. What's going on? Yeah,
so we also offer testing where we uphold confidentiality with our partners or customers. So this means that we won't talk about it. We won't tell anybody what's going on in there.
Oh, so I can't go in today. Well, that's fine. We've got other fun stuff to see.
Let's go see it.
All right. All right, so we're in our Megapod here with our smart pod, and we're gonna do a little maintenance, but it looks like with this technology, we're redefining what PPE looks like in the data center. So today, I mean, even in our lab, our small lab in Cincinnati, we put on ear protection when we've got a lot of systems going on, but now instead we're gonna do hand protection and splash protection, right?
Exactly, yeah. So the fluid is not harmful itself. This is just good lab practice. It stops me contaminating the fluid, it stops the fluid contaminating my clothes.
Okay. Yeah, I guess that this is almost as much for me not having greasy hands as keeping the micro environment of the fluid working properly, right?
Exactly, yeah.
Okay. Awesome. So we're gonna do some service. We got a bad DIMM, right? We gotta fix the DIMM.
Exactly.
How's that work?
Yep. So first step on is to disconnect your Ethernet cable from the top of the central server there.
Okay.
Just pop that off to one side.
All right.
Quite simple now. If you grab that hand on top, you can lift that server up and you can hang it on the hook that's above you.
Okay.
Now you've got 2 options. You can wait for that to drain off. Won't take long. Maybe leave it there for 10 minutes. You can see the fluid dripping off of the server.
Okay.
Or you can go straight in, depending on what you want to do to speed your operations. So we need to replace the DIMM. So this DIMM here.
All right.
Go ahead, take that out.
Okay, so it's still got a little bit of fluid on it, but
Yep.
you can almost just
Simple
like
as
shake
that.
it off and
Yep.
get rid of it. And then now that I've got this dim out, let's say this is out of a retired system that just came out, right? Can this just be cleaned and put into any normal use then because of the fluid, like it's got, it's covered in the oil.
Yeah, so this is a standard dim. No changes have been made to it. You can dry this off using a solvent cleaner.
Okay, and there's going to be
and
no
then
long-term
put it back
effect.
into normal practice.
Okay, so it can be reused, resold, put into any sort of environment that's non-immersed.
If you need to.
Okay, so we've got our new DIM reinstalled into our system. Do you offer like cleaning solutions or anything to maybe repurpose these parts?
Yeah, so alongside our
service?
fluid, we do have a cleaning solution. It's a solvent cleaner that's been made specifically for cleaning of our fluids from the components.
Okay, so it just kind of takes care of everything. You guys have engineered both sides of it on the front and the
Exactly.
back.
Yep.
Awesome. And then I'm looking at this server. This looks like an ASUS server. I see the power supply is there, but I'm not seeing any fans in the system, and it looks like it's ready to blind mate right down into the power down there.
Yeah, it's a good spot. It's an ASUS board, but this is actually a Hypertech server.
Okay.
Hypertech are the ODM in this scenario. And this server has been designed for immersion. It's immersion born. You can now click this off,
Okay.
and if you look at the bottom of the blade, you can see some slots to align the server in, each side of the chassis here. That will hit the power supplies at the bottom and immediately be powered back up. And there you can see the lights coming straight back on.
Yeah.
Reconnect
Get
your
it
Ethernet cable, away you go. System back up and running.
And is there any considerations for the connected interface between the DRAM? Like I just put that DRAM back in, we didn't clean off the slot or anything. It's going to make connection fine and there won't be any
Exactly,
issue?
yeah, exactly, because it's made to work with the fluid. So maybe a small mindset change of having liquids in your data center,
Yeah.
but immersion cooling really is that simple.
And the simple, like I said earlier, the simple change of PPE, just instead of earplugs, we're just going to put something on our hands and make sure we have splash protection, right? So we saw out in the Submarine, the Megapod, we saw two different types of fluids in there. It was the DC-15 and DC-20. I'm assuming that means like data center 15 and data center 20?
Exactly, yeah, so DC means data center, higher the number, the higher performing. DC20 is our highest performing fluid.
Okay.
DC15 has been made with high viscosity to meet certain markets like Asia.
Okay, so they have maybe different requirements as far as the amount of fluid that needs to flow across, or is it a
Regulations.
regulation? Okay.
Yeah, typically insurance regulations.
Okay, cool. So when you guys are engineering these fluids and we're working, we saw all the different types of switches, all the different types of servers in there. You mentioned some stuff about material compatibility, and that extends to more than just what's in the server, but also what connects to the server. You brought out this magical piece here. Can you talk about what happened
so
here?
material compatibility is really important. It's really important we understand what works, what doesn't, what materials you can use and what materials to stay away from. What's in your hand there is a power supply, PVC sheathing. Typically we see with single phase immersion fluids that PVC goes very brittle, very stiff. The plasticizers are removed from the material. Not a problem until you come to need to use it. So you can't flex the cable anymore, you can't unplug it. And if you do flex it, you might even see the outer sheathing material breaks, falls apart, and you're left with open live conductors. So really important that people are educated, understand about material compatibility, and it's been tested and proven to work with the fluid that you're going to use.
Okay, so basically if someone had an incompatible fluid and they went to go unplug their power supply, even though the fluid might not be conductive and shorting it out, they could be grabbing line voltage
Potentially, yeah, and that's a bad scenario. Exactly.
Yeah, that'd be a bad day.
So what we tend to see is that polyurethane sheathing is the best way to go.
Okay, so do I need to buy special cables then to use with immersion, or you guys have been able to engineer fluid around preventing this?
No, so we have suppliers that are ready to bring materials, polyurethane cables. They're on the shelf, they're ready to go. So it's important that when you're working with a fluid provider, you understand which materials or what manufacturers are advised to use.
Okay, and how does that translate into like the networking cables or other like maybe internal cabling inside the systems?
Same scenario. So typically PVC is used in for network cables. We're finding that a polyurethane cable is best to go with that as well, and they're readily available.
On the fluid performance, I gave kind of a wide ballpark out there for what the temperature it's running at. What do you normally see when it's installed? What do you guys test for the temperature window of the fluid in there, and how does that affect system performance?
So typically we're seeing an immersion system operates around 40 degrees. People are looking at elevating that further. We're now seeing 50, 55 degrees even.
So not only will I be able to save a little bit of money on the energy side by removing the fans from the system, which in some cases, I mean, we've seen in our testing 300-400 watts of fans alone, but you're saying that I don't have to spend as much on the cooling because the fluid can operate at a higher temperature?
Yeah, so it's win-win. You remove the power energy from the server by removing the fans. If you imagine a server with a 2,400 watt power supply, for example, could have 500 watts of fans. Almost a 20% energy saving straight away by removing those fans. And the cooling efficiency that immersion cooling brings, it's less pumping power. So it's far easier to capture the heat within a fluid and transfer it than it is air. Okay,
and then at a rack scale, right, so 1Z, 2Z, you know, it's a little bit more difficult, but at a rack scale like we saw in the Smart XLs in the Megapod, what kind of overhead does that incur then with all the pumps and the CDUs and all of that? Where does that sit power-wise?
So the power that the CDUs require for pumping the fluid around is still far less than the fan consumption that would be on an air-cooled server, or even a direct-to-chip server that still has the fans on. If you take one of the rack-based immersion scenarios, so 500 watts of fans are removed, and that's replaced by two 30-watt pumps.
Oh wow, okay. That's pretty big saving. So okay, back to the fluid though. So we're running our fluid in the data center. What's kind of the life cycle expected? Like how long before I need to either add fluid because of maintenance or switch out maybe because you know there might be some sort of bacterial growth maybe that I have to consider? What's that kind of life cycle look like? Can you
so
talk
it's a very good question. It heavily depends on how clean your operations are. Where's your data center based? And you know, are you in a desert where it could get filled with sand, or are you in a hospital kind of environment like data centers are today? But we say fill for life. So the fluid goes through a very easy life cycle. It doesn't get really hot. There's not too many contaminants, which means it's very easy to maintain. That said, we think that the servers might be replaced between 3 to 8 years due to technology improvements, at which time it would be probably best practice to replace the fluid as well.
What happens with the life cycle of the fluid after it leaves my data center? So I'm assuming like my tank provider might come out and help me do that service and complete that, but where's it go after? Is this a forever chemical that's here forever, or what's going on inside the fluid?
So it's not a forever chemical. There's no global warming potential.
Okay.
And we're looking at areas where we can impact and be more than just a fluid provider, looking towards a fluid as a service almost. And one of those areas we're looking at is collection and reprocessing of the fluids.
Okay. What's that look like? Is this kind of like I change the oil in my car and I drop it off at the auto parts store for recycling, or how's that work?
So the detail of how it works is you get to figure it out, and I think we'll end up doing what our customers want us to do in the end, but we're in the infancy of this and looking at different technologies that we can bring to be able to take the fluid from you, look after that problem, and either give it back to you as a refreshed and renewed fluid. Here you can see 4 vials of fluid. This is our fluid DC20. What this demonstrates is fluid on the left-hand side, which is new. This has not been used. And then fluid that has been used. You see the colour discoloration. This could be because of a few things. It could be material incompatibility, where components are leaching into the fluid. It could be that the antioxidant is just working, and that has a colour change associated with it as well. Okay. But through a process of reprocessing the fluid, we can turn it back into the new fluid again. So this new fluid sample, used fluid sample, this has gone through a low energy intensive process where it's then been turned back into new fluid. It's on specification, but the colour still exists. To get it back into removing the colour and turn it exactly back into new, it has to go through a more energy intense process. So this is the kind of research that we're looking at and how we can implement it for use in data centres.
So what would be the difference if I refilled with this one, which has gone through the low versus the high energy processing?
No difference. This is customer perception.
Okay.
Customer perception says, well, it used to be clear and now it's yellow.
Yeah.
But as far as chemically composition is concerned, it's back on specification.
So we're here in one of the test cells with Tom Hughes. Tom's going to tell us all about the AirSys. This thing's pretty cool. It's a similar kind of rack format, but it's got something special going on. What's in here, Tom?
So what we have here is AirSys' liquid rack. Now this is a different type of system, immersion system to what we've seen elsewhere in our facility. The air-assist liquid rack uses spray cooling. So we actually take our single-phase dielectric fluid and spray it onto the servers to cool them down.
Okay, so why would I want something like this versus a tank?
So there's a few reasons, I guess. Firstly, you mentioned it. It's similar footprint. It's what people are used to in a data center, and there's not a huge volume of fluid unlike some of the tank-based systems. So you don't have to have really reinforced floors to deal with the weight of the extra fluid.
Okay, it's a lot lighter.
Yeah, and one of the other reasons is that you can actually run this system a lot hotter.
Really?
So the dielectric temperature in here can go up to 70 degrees Celsius. So that means your water circuit the other side can be around 65 degrees Celsius. So that opens up far more opportunities for waste heat recovery.
Okay, yeah, that's a big topic, is what do we do with the heat these days?
Yeah.
And if you have, I guess, a really good system to use that heat and you need it warmer, right, you'd want something like this. So how are the servers in here? Are they just kind of racked up like normal?
No, slightly different. So the unit has 2 drawers. Each drawer is 25 kilowatts each. And within this bottom drawer, we have 7 Dell PowerEdge servers that are inclined at an angle. The benefit of that is that when you are spraying the hottest components, such as the CPU or GPU, with our dielectric fluid, you get this cascade effect. So you're still getting every part of the server covered with our dielectric fluid, so you still get some residual level of cooling from other parts of the server.
All right, so there's a lot going on in here. I see tubes and cables, and the servers are at that angle that you were talking about. What's going on in here? How does this whole thing work?
So the blue tubes you see here is feeding the dielectric coolant 2 manifolds, which feed 3D printed sprayers onto the hottest components on the server.
Okay, I see. It's kind of like right in front of where the heat sinks would normally sit. That's dousing what? The CPUs?
Yeah.
So the DRAM, the VRMs, the power delivery, all that, right?
Yeah. So these can all be engineered to target the hottest components. So if you've got a really high power GPU, you'd change the setup somewhat, so you're targeting that as well as the other components. So these ones at the moment are just targeting the CPUs.
And what kind of flow rates going through these tubes?
Typically less than 1 liter a second, so pretty low flow, yeah.
Okay. And then are those custom heat sinks that are on there, or are those just the stock?
They are custom made for every server, so depending on what server setup you've got, you'd need to design your 3D sprayers and sort of jet pattern and spray pattern for whatever hardware you've got within the system.
Okay, and then like kind of like the submersion tank, I'm assuming there also has to be some considerations for the thermal interface materials that's used.
Yeah, so same with any immersion system, you need to remove the thermal paste and disable the fans in the BIOS settings so it operates as it normally would. So no real difference there. The only difference is you add in some extra components such as like all the infrastructure you need for the sprayers.
Where's the fluid level sit in this guy?
So the fluid level within this is really quite low. You can sort of see on the screen there is indicative as to where the level would be approximately. These servers aren't submerged in the fluid at all. It's all sprayed on and it trickles off to the bottom. So with this system, you use about 20 to 25 liters of dielectric coolant. So compared to the other tank systems we've seen today, a lot less dielectric fluid is required.
So these they're on an angle, they're face down, the rails look like there's these blue knobs. How do I get these things out of here? What's that look like?
So when it comes to serviceability, you would disconnect all your normal connections at the top. You'd release these blue pins, and because each server is on gas-assisted struts,
oh really?
You can quite easily pull them out and service them as whatever you need. And you'd let the fluid run off, and then you could disconnect everything and take it out for whatever servicing you need to do.
So with those gas struts, you almost don't need a crane to go in and service like a DRAM stick because it'll come out?
Pretty much, yeah. All the fluid is collected in the sump at the bottom. That goes through a heat exchanger just on the back of this unit to a water glycol circuit, typically. And that goes to the intermediate circuit just behind me. If this was in a real data center, the hot water would be connected to your normal plant water, and you'd reject the heat to your normal plant on the external of the building.
So data centers are obviously kind of maybe a newer market for what's traditionally a motor oil company, right? But when you talk about EVs and electrification and things like that, how similar is that data center market to the EV kind of requirements that we see?
Yeah, so for us, we kind of get that reaction that this is kind of Castrol's kind of motorbikes and cars and bikes and trucks, and absolutely, and we still do all that. But in the last 10 years, we've evolved to provide the fluids for electric vehicles. And for those electric vehicles, it can be transmission fluids, it can be e-motor coolants, but also thermal management fluids for the batteries that go into electric vehicles. And today's electric vehicles have got a very large battery that sits in between the two wheels and a base plate that sits underneath that indirectly cools the battery. Now what we've developed is a dielectric fluid where you can fully immerse the battery in that fluid to give much better temperature control, and it's that fluid that we've adapted and now applying to the field of data center. So essentially we're adapting and growing that particular application into this new field.
So as we talk about immersion cooling and the fluids that you guys are developing or have developed, and we all understand, I think, air is not enough. There's too much power going through the chips these days. There has to be an alternative. We've got DLC, we've got two-phase, and we've got immersion. Where do you see immersion fitting in the market? Am I buying it if it's for a specific niche use case, or is immersion for everybody, or what are your thoughts on that?
Yeah, great question. I think so. I mean, what we're seeing at the moment is kind of a hybrid situation emerging, where you've got air cooling is still there and still used, and it will still continue to be there for certain applications. Then direct to chip, as you mentioned, is starting to come in, and we can support with fluids for that application as well, and we're active in that space. But then immersion cooling, really, it's kind of those, as you say, those higher powered applications, better cooling,
scale racks.
Absolutely, the amount of power is significant. So as well as that performance benefit, there's also an efficiency benefit, but also a water use benefit as well. So I think some of our customers, the reason they want to go in this direction is because they want to lower the environmental impact of the data centers that are getting built. By switching across to immersion cooling, all that power at the moment, it's about 40% of the power is on cooling. That can drop to less than 5% if you switch across to immersion cooling, and significantly reduce the amount of water that you're using.
The 40% number that you quoted is really interesting, because we've done tests even on small scale on single server, converting them to liquid, and you see a 40% drop on a single server.
Right.
So if you're seeing that across larger installations, I mean, the scale on that, when you multiply that out by racks and racks, you need the power budget now. You need it back for AI. We learned a lot here today at the Castrol Center for Liquid Cooling Excellence, and really appreciate, Chris, you having us out here and spending some time with us, with your team, and really showing our audience what it's all about and what you guys are doing. Seems like a really cool emerging technology. It's definitely got some maturity in there, especially where folks can start going in, and we're excited to see where this goes.
Cool.
So I appreciate your time. Thank you so much, sir.
Thank you very much for coming. Great having you here.